paper which was published 10 months ago. It came out in Nature late December last year. And this is a collaboration with the experimental group of Peter Liljeroth, and the experimental stuff was spearheaded by Shavolin Kesila-Biike. And Adam Foster and Orlando Silveira did the DFT calculations in this work, and me and Stefan Gotzik, we were responsible in the theoretical modeling of the system and interpreting the experimental results to some extent. So I'm with this the declaration, I have to say that I'm a theorist, and if I misrepresent some of the experimental stuff of Peter Liljeroth's group and their great work, it's solely because of my own ignorance as a theorist. But I try to somehow describe the system and the experimental facts as well as I'm able to as a theorist. So the basic idea is that these van der Waals heterostructures could be a new platform for chiral topological superconductivity. Chiral topological superconductivity is, of course, something that people have been searching for probably 30, 40 years already, and there has been number of elemental material candidates for chiral superconductors, and I think that in some sense the jury is still out there whether chiral superconductivity, P-wave superconductivity, exists in nature in elemental materials or in designer materials for that matter. So I think that the issue is still mostly inconclusive. But here today I'm presenting a new platform which shows very interesting and very promising signatures of topological chiral superconductivity. So, like I told you, this talk is based on this Nature article that came out last December. So the basic setup is here. So the experimental groups managed to grow epitaxially a monolayer chromium tribromaide on top of a 2H niobium diselenide, which is a layered superconductor. So this is a 3D superconductor, but actually it consists of 2D layers, which are in some sense extremely weakly coupled layers. Right. And the experimental tour de force in the sample fabrication was that Shavolin managed to somehow grow epitaxially this 2D, or believed to be 2D ferromagnet chromium tribromide on top of 2H niobium diselenide. And what this additional chromium tribromide monolayer here does is that it provides an out-of-plane magnetization on the top, on the area where it's covering the niobium diselenide, and then it possibly also supplies the system with the Rashba spin orbit coupling, because it's breaking the mirror symmetry with respect to the surface plane. So it brings two additional features to the pristine niobium diselenide: the perpendicular magnetization and Rashba spin orbit coupling. And these are, of course, the two ingredients in addition to S-wave superconductivity that people think that provides us a route towards P-wave superconductivity or chiral superconductivity in 2D systems. And here you can see that due to the lattice mismatch of the chromium tribromide and niobium diselenide, there is a certain moire pattern somehow forming on top of the area where the monolayer ferromagnet is covering the niobium diselenide. Right. So here's a kind of a summary of experimental observations. So experimentally they observe out-of-plane magnetization. So this is an experimental fact, and that's magnetization is observed in places where you have this covering by chromium tribromide. Then, with STM they observe a superconducting gap and a mini gap, which is a feature seen on top of the island, which is of the order of something like 30% of the pristine superconducting gap of niobium diselenide. So here, when we are measuring this DI/DV, or where the experimentalists are measuring the DI/DV curve, they see clear signatures of S-wave type gap here. So there is some gap edge signatures, and then there is almost flat part here. And when they are doing the same measurement, DI/DV measurement on the island, they see that somehow the gap edges seem to, or the flat parts seem to shift somewhat inwards. So there is this feature of a mini gap, which is kind of a feature which would be required for a topological superconductor, and the size of this mini gap is roughly 0.3 times the pristine gap on niobium diselenide. And of course, interestingly, when they are measuring the DI/DV at the edge of the magnetic island, so at the edge of the sample, which would be your tentative topological superconductor, they see this type of feature. So they see that inside this mini gap that they see in the bulk, there is strongly enhanced local density of states, which is peaking near the gap center. So this tentatively would be signature of the topological edge mode, which would somehow be traveling around the edges of the sample. Right. And this type of signature, this enhancement in the edge local density of states, or edge DI/DV, is systematically observed on all magnetic islands. So this is not a hand-picked example of a single island, but this is a generic feature in all islands, and that's why it seems to be a very robust feature, which is of course very important. And also this edge signature, this enhancement, is vanishing when the superconductivity is driven out of the system by increasing magnetic field. So when superconductivity disappears, also this type of subgap enhancement here is killed. So that's also, of course, also a good sign for this phenomenon to be topological superconductivity. So putting all of these tentative, very suggestive signatures together, you can very reasonably ask, is this really topological superconductivity? And to somehow answer this question, or to provide at least some partial insight of this question, it's time to now try to theoretically model the system and compare the experimental results to the theoretical predictions. Okay. Tribromide monolayer. And this is motivated by the fact that actually you can observe these 2D YSR states, as Pascal mentioned in his talk, so that for many purposes, at least for the purposes of individual YSR states, this is a 2H niobium diselenide, which is actually a 3D material, behaves very much like 2D material. So this is our kind of a physical argumentation why this 2D description is a very logical starting point. So the relevant degrees of freedom in the theoretical model are niobium d orbitals that are living on a triangular lattice. So we have a triangular lattice, and then we have one pair of spin split orbitals on this triangular lattice. And to somehow mimic the real band structure, we are using third neighbor hopping model, where we get the input parameters for the tight binding model from our DFT colleagues. And in the end, we add Rashba spin orbit coupling and on-site magnetization by hand. So this basic band structure feature without magnetization and spin orbit come from DFT, and then these are kind of phenomenal fitting things that we add, the Rashba spin orbit coupling and on-site Zeeman magnetization, which is a kind of a local magnetization splitting at each site. So here, because this is a triangular lattice model, the Brillouin zone is a hexagon, and it turns out that there are like 3 special points in the Brillouin zone where the Rashba spin orbit coupling vanishes. So the gamma point, K point, and M point. And wherever the Rashba spin orbit coupling is splitting, we see that there is this Kramers type degeneracy. So locally, the band structure near any of these special high symmetry points look like this. And of course, when we add now the magnetization, we open a gap. So we are getting rid of the Kramers degeneracy, and when we are pushing the magnetization even to larger values, we have this schematically this type of band structure near these high symmetry points. And of course, this is the generic recipe of topological superconductivity. So if you have your chemical potential in the band gap, then when you are inducing superconductivity, you have a topological superconductor with this type of dispersion relation. This generic mechanism of having a Rashba coupling plus magnetization plus S-type pairing symmetry has been known since the pioneering works of couple of groups 10 years ago to be really the paradigmatic ingredients of topological superconductivity. Right. So now we have like three points where this topological gap is opening up, and we can see that in the band structure schematics we see that our high symmetry points are here, and the pristine Fermi energy would be somewhere here. So we see that this topological gap opening near the M point is closest to the Fermi level. So these two other high symmetry points, they are much further away from the Fermi level. So it is kind of reasonable to assume that if there is topological superconductivity in this system, it is somehow related to this M point and the topological gap opening at the M point. And there is near at the M point there is in all of these high symmetry points, K and M point, there is a Berry monopole sitting there, and due to the counting of the full Berry flux, we can see that the possible Chern numbers of these gap openings from the high symmetry points are -1, -2, and 3. And here in this interesting topological regime, or in the interesting high symmetry point, the tentative Chern number of this system would be 3. Just due to the crystalline symmetry. And here we see the DFT suggests that the Zeeman gap could be of the order of 10 to 100 millieV. So we don't have really a good handle what is appropriate size, but we know that it realistically could be tens of millieV. And also we see that the Fermi level here without the magnetic islands in the pristine system, it is something like 100 millieV above the topological gap. So somehow we would need this pristine Fermi energy to shift down here. And it doesn't really require that much fine-tuning, because this topological gap is then sizable. So if we have somewhat down, a little bit of downward shift of the Fermi level, then we are in the topological gap, and our system is tentatively, it is a chiral superconductor with Chern number C. And indeed, this Fermi level shift due to the magnetic contact material is expected. So obviously the pristine system Fermi level is changing, and it is due to the chemistry of these materials. You would even expect that it's the same. It's in the correct direction, that it would shift downwards. And actually, even the experimentalists see that there is comparable downward shift of the Fermi level in this system. So the band structure of this chiral superconductor at C equals 3 would look like this. So there are 3 pairs of chiral edge modes in the topological gap. And when we do the comparison, this DI-DV comparison, moving from the island towards the pristine system, crossing the boundary, the experimentalists see this type of a zero or in-gap structure of the DI-DV. So when you are at the boundary, you see this edge mode enhancement, or something that we think that would be the edge mode enhancement. And when you move into the clean system, then this disappears. And this is the experimental data that you see. And here is our simulation data based on the model here. And basically you see that the simulation results are very well somehow qualitatively in line with experimental findings. There are a couple of things that are not quite seen here. So here in the real experiments, there seems to be a modulation of the edge mode intensity, and this modulation has the same periodicity as the Moire pattern. And in the theoretical model, we didn't implement in the first modeling, we didn't implement the Moire pattern. So there is, I think that the reason why and there are also follow-up experiments and modeling which strongly suggest that this type of enhancement and suppression, which is periodic, is due to the Moire pattern. And one thing that I want to emphasize here is that it doesn't mean really that there is a break in the edge mode. It's just that there is such a strong suppression of the signal that it drops below the sensitivity of the measurement. So it is always there, but it's just you just don't see it because there is such a strong suppression and enhancement here going on. Okay, so here's my conclusion. So chromium tribromide or niobium diselenide 2H niobium diselenide structure combines a monolayer ferromagnet with a layered superconductor, and the experimental findings in these systems are in very good agreement with topological superconductivity. And of course, as a community in the last 5 to 10 years, I think we have learned some humility in our declarations of topological superconductivity, especially considering the rocky road in the nanowire experiment. So it's better to somehow be a little bit reserved, even though there seems to be a pretty good match. And there are some loose ends which require extra work also in this system. So one thing is the edge mode modulation that I already mentioned. And then there is this issue of moderate fine-tuning of the Fermi level that should happen in order to get the topological superconductivity. And in the follow-up work of Peter Liljeroth's group, where I'm no longer a part of this collaboration, there is a possible answer to all of these, or both of these issues. And if you include also the Moire pattern that is very clearly seen in the experiments, that will give you, at least in theoretical model, that gives you exactly the similar edge mode modulation that they are seeing in experiments. And also the Moire pattern gives rise to a band folding, which also kind of, it opens up more topological regimes, so that it also mitigates this moderate need for Fermi level fine-tuning into a topological gap. So that was it. Thank you for your attention.
Thank you.
This in some sense, this is much more complicated system than our theoretical model is taking into account. So of course there is, at higher energies, there is this charge density wave stuff that could somehow affect something also, and then this contact between the magnetic layer, the chromium free bromide monolayer, and the surface of the niobium diselenide. It's very difficult to somehow quantitatively get the correct spectrum, and this anyway our theoretical model is kind of a caricature which is somehow just taking into account the most dominant things there. And I would also say that it is kind of a logical first try. So there is definitely a lot of room to try to improve the theoretical modeling. Okay. So this is a question which is asked quite a lot because, okay, so density, if we have density of states, that would be, the density of states would be almost constant inside the mini-gap. That's what you would expect. But here we should, of course, understand that this DIDV is local density of states, which combines two features. So it, of course, reflects somehow the density of states and the wave functions. And this means that the fact that this looks like a zero bias peak, even though there are dispersive modes, just mean that okay, so here, right. So it means that the edge modes at the center of the gap are more localized to the edge. So that if you are measuring a local density of states close to the band edge, those modes are somehow penetrating into a bulk a lot more than at the center of the gap. So the fact that it looks like a zero bias peak means it can be translated to the fact that the penetration depth of the edge mode at the gap center is much smaller than when you are going towards the edge of the gap where they are becoming more and more delocalized. So that feature of the wave function means that you actually see this type of peak structure, and it's not constant like the density of state is.
Okay, thank you. So I could also imagine that it's because you have some confinement along the edge, right? Then you also have standing waves. Yeah, I mean you can still have some scattering, which could also result in some kind of peak-like signal, maybe.
Yeah, sure. I wouldn't somehow bet my life that this is topological superconductivity. It's just like it's very suggestive, and it is at the moment it's more difficult to figure out what else it would be than this.
Mm-hmm. Okay, thank you.
Okay. We have time for a very last short question, Denis.
Yes, thank you very much. I would just like to make a more general comment, like from one theoretician to another. You have said that you have an effective 2D calculation, but as a matter of fact, that is probably all you need, because a student of mine and I have published a paper this summer where we show that the Hohenberg-Mermin-Wagner theorem is completely ineffective in 2 dimensions for superconductivity. The sample would have to be larger than the universe for the observable for the fluctuations, infrared fluctuations, to suppress the order parameter. In other words, there is much more space for 2-dimensional superconducting fabricated materials than people ordinarily think, and I would like to encourage everybody to try to kind of fabricate such materials. So this, I think, is a perfectly good avenue to start. I'll put the reference on the chat to everyone if someone is interested.
Thank you.
Yeah.
Thank you. So I guess we should thank the speaker again. Thank you.